Dear students, today we will discuss the linear independence and dependence of vectors. So what is linear independence and dependence? So we will start from the definition. So let V1, V2 up to Vn be a set of vectors. Okay, and alpha 1, alpha 2 up to alpha n are corresponding scalars. So if you take its linear combination, so its linear combination is alpha 1 v1 plus alpha 2 v2 up to alpha n vn. Okay, so this is the linear combinations. If alpha 1 v1 plus alpha 2 v2 up to alpha n vn is equal to 0 vector such that all alpha I is equal to 0, then implies v1, v2 up to vn are linearly independent. So this is the definitions. If alpha 1 v1 up to alpha n vn is equal to 0 vector such that all alpha I is not equal to 0, that means some may be 0, some may not be 0, alpha I not equal to 0, then v1, v2 up to vn are linearly dependent. This is the definitions. Okay, so now we will consider different examples and different cases to test the set of vectors are linearly independent and dependent. And when we will test the linearly independent and dependent, during that period also I will explain what is its geometrical significance. Now we will discuss different methods to test linear independence and dependence. There are three methods to test linear independence or linear dependence. So there are three methods. First method is proportionality method. Second method is definition method. Third method is vector method. So now we will discuss proportionality method. Okay, so let us consider three vectors. So let v1 is equal to 1 2 3, v2 is equal to 2 1 3, v3 is equal to say 2 4 6. So these are the three vectors. Compare v1 and v2. If you look at its components, that is 1 by 2 is not equal to 2 by 1 is not equal to 3 by 3. Means its corresponding components proportionality are not same. This is 1 by 2, first component. This is second component 2 by 1, which is not equal to first component ratio. 3 by 3, which is also not equal to first and second. So if this happens, so that implies v1 and v2 are linearly independent, right? That means if we consider these two vectors in three-dimensional vector space, these two vectors will cut each other. So linear independence means its geometrical significance implies v1 and v2 are intersecting in vector space. Okay, in three-dimensional space, these two vectors are there and they will intersect. That is the geometrical significance of the linear independence. Then come to v1, v3. Compare v1 and v3. So here 1 by 2 is equal to 2 by 4 is equal to 3 by 6 is equal to constant. Okay, so that implies v3 is equal to 2 v1, or we can say a vector is written as some constant times v1. Okay, so when we are able to write a vector as the constant times of another vector, so implies v1 and v3 are, here we write v2 equal to k v1, so that implies v1 and v3 are linearly independent. Okay, so when one vector is proportional to other, that indicates linearly independent. And what is its significance? its significance is if we draw these two vectors in vector space, they will not intersect, rather they will be parallel. Now we will consider another example by considering several vectors, and we will test the definition techniques to test whether the set of vectors are linearly independent or not. So V1 is equal to 2, 3, 1, 2, V2 equal to 3, 1, 1, 2, and V3 equal to 7, 7, 3, 6. Okay, so we will test these three vectors whether they are linearly independent or not. Test linear independence or dependence. So let alpha 1, alpha 2, alpha 3 are corresponding scalars. So alpha V1, alpha 1 V1 is equal to 2 alpha 1, 3 alpha 1, alpha 1, 2 alpha 1. Alpha 2 V2 is equal to 3 alpha 2, alpha 2, alpha 2, 2 alpha 2. And alpha 3 V3 is equal to 7 alpha 3, 7 alpha 3, 3 alpha 3, 6 alpha 3. Just we are multiplying the corresponding scalars to each component. As per definition, alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 is equal to 0. Implies 0 means it is a 0 vector. 0 vector means it will have 4 components. Okay, so that means we can write it as 0, 0, 0, 0 vector. Right. So the first component we add, that is 3 alpha 1, sorry, this is 2 alpha 1 plus 3 alpha 2 plus 7 alpha 3 is equal to 0. Next is 3 alpha 1 plus alpha 2 plus 7 alpha 3 is equal to 0. Then alpha 1 plus alpha 2 plus 3 alpha 3 is equal to 0. Then 2 alpha 1 plus 2 alpha 2 plus 6 alpha 3 is equal to 0. Means as per this we add this vector, this vector, this vector. When we add these three vectors, the corresponding components are added up. This is first component, this plus this becomes 0. Then 3 alpha 1 plus alpha 2 plus 7 alpha 3 becomes 0. Then alpha 1 plus alpha 2 plus 3 alpha 3 becomes 0. 2 alpha 1 plus 2 alpha 2 plus 6 alpha 3 becomes 0. Okay, so now what we get? So this is a homogeneous system of equations. Okay, and once we get the homogeneous system of equations, you know how to solve a homogeneous system of equations, which we have already discussed in my previous video. I will give the link below. That is solution of homogeneous system of equations by Gauss eliminations. You can refer it. Now for this system of homogeneous equation, consider the corresponding matrix. That is 2, 3, 7, 3, 1, 7, 1, 1, 3, 2, 2, 6. So that is reduced to the new matrix as 2, 3, 7, 0, minus 7, minus 7, 0, minus 1, minus 1, 0, minus 1, minus 1 by the row operation 2 row 2 minus 3 row 1, this is for second row, 2 row 3 minus row 1, this is for third row, and row 4 minus row 1, this is for fourth row. Okay, so that gives 2, 3, 7, 0 -7 -7 0 0 0 0 0 0. So that is row 3 7 row 3 minus row 2 and row 4 is 7 row 4 minus row 2. After doing all these row operations, now the law says, after the row operations, now we will draw the conclusion. If number of non-zero rows less than number of unknowns implies then the set of vectors are linearly dependent. This is our first. Then second, if number of non-zero rows equal to number of unknowns implies set of vectors are linearly independent. So these two lines you have to remember as a rule or formula. For this problem, here you see how many number of non-zero rows are there? Are two number of non-zero rows. How many variables are there? Alpha 1, alpha 2, alpha 3 corresponding to alpha 1, alpha 2, alpha 3 are the scalars. Corresponding to three scalars, there are three vectors v1, v2, v3. As here number of non-zero row is less than number of variables implies the system of the three vectors v1, v2, v3 are linearly independent. Sorry, this is linearly dependent. Again I am repeating, this is the law. Okay, now you come to the concerned problem. In concerned problem, how many number of non-zero rows? Two number of non-zero rows. What are the scalars we have considered? Alpha 1, alpha 2, alpha 3. Why we have considered three scalars? Because there are three vectors, right? So number of non-zero row 2, number of vectors 3. So 2 less than 3. So this is this case, less than. When less than, so the vectors are linearly dependent. That means v1, v2, v3 are linearly dependent. Suppose we will have a problem that after row operation we will have three non-zero rows and we are having three scalars alpha 1, alpha 2, alpha 3 corresponding to their three vectors. As number of non-zero rows will be equal to the number of vectors, in that case it will be linearly independent. Is it clear? So by concluding these two, we say whether the vectors are linearly independent or dependent. Now we will consider the third case or the third technique by which we will test whether the set of vectors are linearly independent or dependent. And that method is the most simplest one and most convenient to understand and most easiest to use to test linear independent and dependent. I have explained you all these three, but it is your choice for the exam point of view which method you will apply. So let us start with one example. v1 equal to 2 3 1 2, v2 equal to 3 1 1 2 and v3 is equal to 7 7 3 6 7 7 3 6. Okay, so these are the three vectors and we will test whether these three vectors are linearly independent or dependent using the matrix technique. Okay, solution. So you make a matrix by considering each vector as a row vector. So that is 2 3 1 2 3 1 1 2 7 7 3 6. So this is the matrix what we form by using the vector. Then give the name of the vector in the right hand side. This is v1, this is v2, this is v3. Okay, so this is our step 1. Then step 2. Step 2, use the row operation like Gauss elimination 2 3 1 2, then you make this 2 as 0. Okay, so this is our v1. How we will make this 0? This is 3, this is 2. We will multiply 2 to this and multiply 3 to this, then subtract. That is, for this v2 we will have 2v2 minus 3v1, and for this we will multiply 2 here and 7 here, then subtract. That is 2v3 minus 7v1. You see, we are operating always with 1, that is v1 v1. So what it gives? By this row operations, we get row 2 as 0, minus 7, minus 1, minus 2. And by this row operation 2v3 minus 7v1, we get 0, minus 7, minus 1, minus 2. Then again you go for step 3, that is 2, 3, 1, 2, 0, minus 7, minus 1, minus 2, and this is 0, 0, 0, 0. So this is v1, no change. This is 2v2 minus 3v1, no change. Now how this is formed? This row minus this row, that is 2v3 minus 7v1 minus this row, that is 2v2 minus 3v1. Okay, now we will draw the conclusion. If after the all row reduced form, after all row operations we will get a row reduced form. If in the last step we get a 0 row, then how that 0 row is formed? With the help of this. So you write this is equal to 0. If we are not getting 0 row, we will not write. If we are getting 0 row, you write the corresponding expressions. So now we get 2v3 minus 7v1 minus 2v2 plus 3v1 is equal to 0. Then again simplify. That gives minus 7v1 plus 3v2, that is v1, that is minus 4v1 minus 2v2 plus 2v3 is equal to 0. Actually what it says, you see, we have considered three vectors v1, v2, v3, and this is nothing but the linear combinations of v1, v2, v3, right? So it is scalar minus 4, this is minus 2, this is 2, and scalars are not 0. As linear combinations are 0 and scalars are not 0, so implies v1, v2, v3 are linearly dependent. The case where we will not get 0 row, in that case we will say the set of vectors are linearly independent. This is all about the idea that how you test the linear independence and linear dependence in three different methods.